turn on this computer. It's recording.
Okay, so can everybody see the Planetary Sciences screen there? Okay, all right.
All right, I'm leaving. Bye.
Thanks. All right, thanks. There's Jason right there, help me out, save my butt there. Anyway, yeah, so again, sorry about that. Let me just restart this again. My name's John. I'm a planetarium operator. Normally, I would do shows on the Saturdays before pandemic. Now, mostly doing stuff from home, but I'm here doing some classes tonight. So today we're going to be learning about planetary science, just going overview of the solar system. And since we got a small crowd tonight, I'll, you feel free to ask me questions. So first, we're starting off with an overview of our solar system here. Wait for the screen to come up. So, going to zoom into our solar system itself. The solar system, at its basic level, of course, is our sun, which is a star, a large ball of hydrogen helium gas burning on space. Beyond that, here we're looking at the creation of the solar system. The sun began in a large nebula of hydrogen helium gas, slowly condensing down into a ball under gravity till we get this object you see here, which is a star, which is a small protostar, a baby star surrounded by a swirling ring of dark gas and dust, which will eventually become the planets of our solar system. Like you see happening right here, this is a early baby planet also called a protoplanet, with its own little ring of gas and dust swirling around it, being pulled together by gravity. As we zoom in here, we see our own sun, like a model of the young sun forming. These are bits of early protomatter, chunks of rock and dust that have condensed down out of this early embryonic cloud, forming together, condensing down into the planets, pulled by gravity, compacted into a tighter and tighter ball, until eventually we reach the sun. It's faded up here. So here we have our sun, much dimmed, so we can actually see it. These dark spots on it they're called sunspots, which are relatively cooler areas in the sun. I mean, they're still hundreds of degrees, but compared to the rest of the sun's surface, they are significantly cooler. From here, we are going to pull back to see the inner planets of our solar system, Mars, Earth, Venus, and Mercury, which are known as the terrestrial or rocky planets. Beyond this, we have the asteroid belt. Oops. Go back to those main planets. Oops. The video just cut off for a sec there. One sec. Where did you go? Oh, there we are. It zoomed in way too much, that's why. So I think it did. Whoop. Let's try that again. Let's try that again. Here we are. There it is. All right. So actually, let's reset us back to the solar system here. So we're taking a view of the solar system. It wants to cooperate.
Yeah, you've got like a little slice of your Uranus, but you don't.
Interesting. Let me try cutting back to this. Sometimes you get glitches like this, so we'll reset to the beginning there. All right.
Yay.
There we go. Back to the sun. There we go. Let's pull back to the asteroid belt. System is giving me a great time tonight.
Don't worry.
It's all good.
I think Jason
Yeah,
said
don't worry.
Jason
Yeah, no
said
pressure.
they just did like a reset on their system, I guess. But anyway, we'll make do with what we've got here. So beyond the terrestrial planets, we have the gas giants and ice giants, also sometimes called the Jovian planets: Jupiter, Saturn, Uranus, and Neptune. Jupiter and Saturn are, again, what we call gas giants, which are mostly made out of hydrogen and helium. The Uranus and Neptune are also sometimes called gas giants, but they are actually, or more correctly known as ice giants, which is because they are composed mostly of like hydrogen, helium gas, but they also have like various types of frozen ice in their atmosphere, like frozen methane, frozen ammonia, frozen cyanide, frozen carbon dioxide. So they're like a mixture of gases and gas and ice. Now, if we pull back beyond the gas giants and the ice giants, we get to what is known as the Kuiper Belt. The Kuiper Belt is an area of like rocky bodies, or most rocky and icy bodies, forming a rough ring around our solar system. They are this is actually where like a lot of the what we call dwarf planets originate, like Pluto, Eris, Haumea. Bring them up right there. They all orbit around this big ring of icy outer planets. And then as we pull back from that, we get to what's called the Oort cloud, way, way, way out, far beyond anything else in the solar system. All right. Oh, and I did that again. The Oort cloud just shut off on me. Don't know why. There it is. Sorry, one sec here. Gotta go back to that. And
Did you say it was wart? The wart?
OORT. It's a,
Oort.
I believe it's a Dutch name.
Okay.
Let me just pull out that there. There we go. That's just, but anyway, yes, this is the Oort cloud, which is a large cloud of, it's more frozen objects. This is actually where a lot of the comets in our solar system originate. The Oort cloud is just a big cloud of almost all ice. The size of it is, it's just far beyond any of the orbits of the planets. Beyond the Kuiper Belt there, you can see that little circular ring in the middle there is, we're part of the Kuiper Belt, Kuiper, Kuiper Belt is. And within the Oort cloud, you have like large, what are basically dusty snowballs. Those are the comets. And occasionally they will be sucked into a gravitational orbit where they will be pulled in towards the inner solar system and orbit past the sun, sometimes coming close enough for us to see them from Earth. So when you see something like, the Halley's Comet, or in the 90s, there was the famous Hale-Bopp Comet, those are voyaging bodies coming in from the Oort cloud, circling near the sun and going all the way back out. Now, I mentioned with the Kuiper Belt, we talked about, called them dwarf planets. And I know there was a lot of controversy a couple of years ago when Pluto was downgraded from a planet to a dwarf planet. And there is a specific astronomical reason for that. I mean, the planet itself obviously hasn't changed, but the definition of what a planet is had to be altered. So the International Astronomical Union, which is this governing body for deciding body for astronomers throughout the world, they had to define a planet as a celestial body that orbits around the sun. So a moon wouldn't be a planet because it orbits around a planet.
No.
A planet has sufficient mass for its gravity to squish it down, which means that it which means that its own mass and gravity pulls it down into a tight ball, because there are comets and asteroids out there that are big lumps, kind of shaped like potatoes, so they wouldn't count as a planet. And then this is the reason that Pluto was designation was changed. A planet has cleared the neighborhood around its orbit of debris, meaning that it's just like swept out all the comets and asteroids and all the debris around it. But with Pluto, it still has debris floating around it. So that's mainly the reason it's not considered a planet, because it has other stuff swept around it. Now, the reason that they did this, that they changed it from a planet to a dwarf planet, was because they discovered the dwarf planet Eris, Eris, which is appropriately named for the Greek goddess of discord. Because when they discovered Eris, they were trying to decide, do they call this a planet? Because it's a large mass, spherical mass, and it's orbiting the sun. But from Eris, they also found that they kept finding dozens of other objects of this size floating around in the Kuiper belt. So they had a choice. Astronomers were trying to decide, do we add dozens of new planets to the solar system, or do we give a new designation? So it's really more of a classification thing. They label these new planets like Eris as dwarf planets, and then Pluto went into that category of dwarf planets. So it's still a large body orbiting the sun. It's just that it's got a new cool designation.
Can I ask you a question?
Absolutely.
So when you say, you're saying it hasn't cleared the neighborhood around its orbit, is 2 linked to 3, meaning that if you're not clearing the neighborhood around your orbit, that means you don't have sufficient mass for self-gravity, or does it have any relationship to that? What prevents the planet from clearing the neighborhood around its orbit?
That is basically it, is that it's not large enough for its gravity to have swept up everything around it. Like Pluto is not big enough to have sucked up all the debris around it. Whereas like planet, like even planet of Earth size, it's big enough that anything that's in its orbit has been sucked up and or cleared away or pushed away. But yeah, Pluto and the other dwarf planets are small enough that they haven't done that yet.
So they're more gaseous planets.
Well, it's more that their size, because Pluto is mostly made out of ice and a rocky core, but the gas giants, which are mostly gas, they are actually so big that even though they're made out of gas, they actually have such big mass that their gravity has actually sucked up
everything. Yeah. Okay. Thank you.
Now, one thing I want to talk about is distance in space. So let's jump past some of this stuff here. A big important thing for planetary science is measuring how far away things are in space, which is the basic unit that we use is called an astronomical unit, AU, which it roughly measures the distance of the Earth to the sun, which one astronomical unit is the average distance that the Earth is away from the sun. The Earth is actually on an elliptical orbit, so its distance from the sun can vary. So we kind of took the average of that and use it as an astronomical unit, which is useful for measurements. Like we can say that I believe Mars is about, I think, 3 astronomical units from the sun. So it gives you an idea of scale. Now, the way they calculate astronomical units is, well, it's a lot of, Get screen come up for me. It's really a lot of involved math, really more probably when we talk about here. But basically they did it through through triangulation, where you could measure. They actually first took calculations by measuring the transit of Venus across the sun. If you watch Venus, Venus is this little dot here. You can see slowly moving across the sun. Early astronomers looking at the sun with a telescope, using very thick filters, of course, to not burn their eyes out, they were able to observe Venus moving across the sun. And so they were trying to measure like how far away is Venus from Earth and from the sun. So what they did was they'd have astronomers would go to two distant points on the Earth, say Paris and like Rio de Janeiro, and they would measure Venus transiting across the sun from their two angles, from their two cities. They would take precise readings at specific times. And then later on, the astronomers would meet up and they would compare like what time did Venus cross the sun according to them, because it's something known as parallax, which is where parallax is where if you're looking at an object at two different angles, if like say you and a friend are staring at like a telephone pole, two different angles, you see the telephone pole and you see another like a tree behind it. Based off of your angle, the tree seems to not really move, but it seems you view the telephone pole at a different angle relative to the tree. So if someone is standing over here and the telephone pole is in front of you, you'll see the tree directly behind it. But your friend who has moved over a bit will see the tree moved over to the right. So that is what's called parallax, which is the movement of a distant object compared to a closer object, which again, astronomers use that in space to measure how far objects are. Again, a lot of complicated math, but with the transit of Venus, two people watching Venus go across the sun from different points on the Earth, they would see it cross the sun at different times. So through a lot of math, comparing like the times and the distances, they were able to figure out the angle that they were viewing Venus at, and they were able to form a triangle. And using trigonometry, with that, they were able to figure out the angle from Venus to Earth, and from there figure it out to the sun. So a lot of kind of involved math with that, but it gives you a basic idea that using just trigonometry and measuring transits and a lot of other observations in the sky, they were able to figure out a rough estimate of the astronomical unit. And since then, of course, in the modern age, it's been refined much more. So we have an exact measurement, and we're able to use that to measure the distance to other objects. So let's fly out here to one astronomical unit away. This is again approximately the average distance of Earth from the sun.
Wow.
But now we'll fly out to here. We're moving out to about the distance out around where Neptune is. So Neptune is approximately 45 astronomical units from the sun, which means that it would take it's 45 times the distance that Earth is from the sun. And then that you can measure that out all the way into the Oort cloud. At a certain point, if the distances are so far away that we have to start using other numbers to measure. Like when we get out beyond the solar system, when we measure the distances to other stars, we start measuring in terms of light years. And a light year is making a lot of involved math, but a light year is the distance that a beam of light travels in a year. So, which is the famous Einstein's equation, E equals mc squared, helps us figure that out. So, but you say a planet is, or a moon, like a star is say 4 light years away. What that means is the light from that star has been traveling towards Earth for about 4 years. So when you see the light hit us, we're actually seeing the light from 4 years ago, because it's taken the light that long to get to us. And at that point, light year is a very useful measurement for space because you can measure huge distances. So we'll get out to like stars that are like 3 million light years away, which means the light from that star has been traveling for 3 million years before it hit Earth. So we're actually seeing the star as it looked 3 million years ago. it gets into a lot of interesting time space stuff.
That's cool.
But we're focusing in today on the planets. So here we are talking about mass, which is compared to Earth. Now, mass is the amount of matter within an object, of course. So the terrestrial planets, Earth, Venus, Mars, and Mercury, they're more compact. They're stony, but they don't tend to have as much mass. The planets that have the most mass are the ice and the gas giants, because even though it's gas and it's relatively thin, spread out, there's just so much gas there that it just gives them an enormous amount of mass. Plus, the ice giants there have an even higher amount of mass. Let's see here. Now, related to mass is we have density. Density is, well, how tightly packed all that matter within the planet is. Now, Jupiter and Saturn may have more mass than Earth, but they are less dense than our planets. So even though they have tons and tons of gas, if you were to take like a square or a cube of Jupiter and a cube of just anywhere in Earth, the cube of Earth is much denser, much thicker than the cube of Jupiter, because that cube of Jupiter is just, again, like a cube full of gas, whereas Earth, it's a cube full of rock. It's just that there's so much more of it on Jupiter. So looking at the densities here, the gas giants may be bigger, but they're actually overall lighter than our planets. So you have Earth, one of the densest planet, or they're overall denser, I should say, but Earth is the overall densest planet in the solar system. Then Venus, Mercury, and Saturn is actually one of the least dense planets in our solar system. There's a common astronomical anecdote that if you had a glass of water big enough, you could actually float the planet Saturn on its surface because it's less dense than water. You'd have to have a giant glass, but you could do it. All right. See here. All right. So again, here are our terrestrial planets: Earth, Venus, which is often called Earth's twin, mainly because it's the same size. It's certainly not at all like Earth in terms of the climate, because Venus is very hot and it's got real thick cloud cover. You've got Mercury, which is a small planet, not much bigger than our own moon. And you have Mars, which is cooler than Earth and only about a third the size. Then you've got the Jovian planets. You got, again, Jupiter, Saturn, Neptune, and Uranus. From here, I want to talk a little bit about the atmospheres of all the planets. Every planet, when they were first forming in that big cloud of gas and dust, they did develop an atmosphere, which was just the gas that was pulled in around the core of the planet and just kind of remained in the air. All of them started off with an atmosphere that was mostly hydrogen and helium. But and the gas giants have all retained that hydrogen and helium. In fact, it makes up most of their surface, or it composes most of their atmosphere. But the terrestrial planets actually, they developed what's called a secondary atmosphere, which is where the hydrogen and helium was replaced with other gases. On Earth, most of that is nitrogen. There's of course the oxygen we breathe mixed in there. Venus is mostly carbon dioxide with a little bit of nitrogen. Mars is mostly carbon dioxide. And Mercury is mostly oxygen with sodium. Now, these other gases on the terrestrial planets actually come from inside the planet. They come from volcanic activity. They come from gases escaping the rocks of the terrestrial planet. And on the case of Earth, they actually come from plants and algae producing oxygen and spreading it into the atmosphere. But with the gas giants, there was no volcanic activity to replace the surface, and there's no life to produce oxygen in the atmosphere. So they've retained that original atmosphere. Now, Now, Earth still, of course, is the one planet with the thickest atmosphere, which is the one we survive on, we can breathe. Venus has an atmosphere that's even thicker than Earth, but it's actually almost like soup. If you were to somehow land on the surface and survive, it would be like pushing through like a thick chowder because it's just the atmosphere is so thick. Of course, the atmosphere is mostly carbon dioxide and sulfuric acid, so it not a very pleasant place to be. Now, Mars and Mercury have actually lost a lot of their atmospheres because they are smaller than Earth and Venus. So because they were smaller, their gravity, they didn't have as much of a gravitational pull as Earth and Venus. So because they had less gravity, their atmospheres were gradually drifted off into space because there's nothing to pull them down. So let's close that here. Now the Earth's atmosphere, of course, is the one that's most studied, and the one that is the most complex. The Earth's atmosphere is divided into a couple different layers. You've got it all the way at the bottom, the troposphere, which extends from the ground up about, let's see here, extends up just above the ground, about a couple miles. And that is where most weather and precipitation occurs here. So that's where the vast majority of our clouds happen. And as you go up in the troposphere, it gets colder and colder. Beyond the troposphere is the stratosphere, which contains the ozone layer that protects Earth from cosmic rays. Now here, weirdly enough, it gets warmer the higher you go up because of the radiation, like the radiation from space collecting there. Now, the jet streams tend to flow at the boundary between the troposphere and the stratosphere. The jet stream is like the super fast winds blowing around like the Arctic Circle in the Antarctic that just whip winds around at those levels. Above the stratosphere is the mesosphere, that's where you tend to get a lot of the meteors and if you get meteorite flashes. When meteors fall to Earth, they burn up in the mesosphere, so you get that bright flash of a shooting star. And again, here it starts to grow colder again. So you go troposphere, gets colder as you go up, stratosphere gets hotter, and then mesosphere gets colder again. Now the thermosphere, which is above the mesosphere, and it's a lot thicker, that's where that is where most of the solar radiation is absorbed. The stratosphere gets the last stuff that gets towards Earth. But the thermosphere is an area where most of the satellites orbit around Earth. So they're high enough up that they aren't sent crashing to Earth, but they are still caught in our gravity at that level. And then right above that is the exosphere, which is a very, very thin layer that's basically where the Earth's atmosphere fades off into space. And there's no real set boundary for that because the air just gets thinner and thinner and thinner as it goes up until it's space. Now, Mars, again, does have an atmosphere. You can see it from this picture here. Again, it's much thinner. It doesn't have as many, it's not as well studied, so we don't know how many layers it has, but it definitely does not have as many complex layers as our planet does. The air, of course, is not very hospitable to humans. There's not really nothing to breathe there. So here it actually is a photograph taken from the surface of Mars. You can see here that the sky is very diffuse and very pale. And there's also a lot of fine dust in the air, which gives it this kind of overall milky quality. Now Venus, as I said before, Venus's atmosphere is nearly all carbon dioxide. However, it's got much thicker layer of carbon dioxide than Mars. Did I lose everybody? Can everybody still hear me?
Yep.
Okay, cool. I want to make sure it wasn't falling out again. Okay, so Venus's atmosphere is like Mars, is mostly carbon dioxide, but it's much, much thicker on Venus. I said it's almost like soup. And it's got these very dense clouds, which are mostly made out of sulfuric acid, covering the surface of the planet here, which also tends to rain. It also rains down on the surface as like a perpetual sulfuric acid rain. Let's see. One sec. Right.
What's the temperature on that planet? Is it,
On Venus,
yeah,
it is. Venus is approximately. Let me see here. It's several hundred. I read the exact number, but it's several hundred degrees. It's enough that it will actually melt steel, because the carbon dioxide is basically like a runaway greenhouse gas.
wow.
So I forget the exact number off the top of my head, but I know Russia sent a probe to land on Venus, I think in the 80s. It got down to the surface, took one picture, and then it literally melted because of the temperature fused all the metal together, and then the acid rain finished it off. And this here is an artistic impression of what the surface of Venus looks like. The pictures I got back in the Russian probe are actually facing towards the ground, so it just shows us this rocky surface. But this is a rough idea. This is an idea of what you'd be looking like, what you'd be seeing if you were standing on the surface of Venus looking up. You'd see these real thick yellow clouds and just a flat landscape, mostly made out of lava, because Venus is actually very volcanically active. Let's all right. Move that down. Okay, so now we've got here the surface of Jupiter. Again, is mostly hydrogen and helium, but it has other things, other gases mixed in with there. Let's see. The other gases it has mixed in are like trace amounts of ammonia and other gases like that. And those are actually what give the color to Jupiter's surface here. What you've got are Jupiter's surface here. You have ammonia ice crystals that create the dark belts there, and then the bright areas are called zones. And what's happening here is the excuse me. The bright areas called zones are where the gas is rising up, and then the dark belts are where it's sinking up again. So there's like a storm effect going on. Gas is rising up from deep inside and then streaming back down again, growing darker. And this creates some really nice, intricate patterns here. This is an actual picture of the surface of Jupiter. These swirling clouds here. Let's see. Just that. There we go. Yeah, so these swirling clouds here are just those huge, humongous storms on the surface of Jupiter. You see swirling around there. They're all getting made out of crystals of ammonia. This here image is, the color's a little bit enhanced, but this gives you a good idea of what they look like.
So if you were underneath those clouds on the surface, would it look just like that, or would it look that crazy looking up from underneath?
Underneath, you probably wouldn't be able to see very far, unless you were in like a really thin area, because you'd just be enveloped in these huge swirling clouds. Your vision would be, it would be kind of like being in a thick, fast-moving fog. These clouds are actually moving at hundreds of miles an hour. Like this picture makes it look like they're serene, but they're churning like at much faster than any hurricane on Earth. So if you were floating down there inside the atmosphere, you'd just be seeing these colorful swirls of clouds just whipping by you hundreds of miles an hour.
Oh.
One of the most famous clouds on Jupiter here is the Great Red Spot, which is, again, it's a huge hurricane that's about 3 times the size of Earth. And it's been around for at least 200 years, probably more, but we first observed it about 200 years ago. So
it just doesn't move. It just stays there. Is it just, I mean, why wouldn't it move if there's so much motion with the clouds and all of that?
well, it does. I mean, it moves. It orbits on the surface, but we actually, to be honest, we actually aren't exactly sure why it hasn't like dissipated or why it hasn't shifted around. One explanation we think is that because there's no surface below it, like there's no rocky surface inside there, it's all clouds almost all the way down. One theory is that because of that, there's nothing on the ground, there's no ground to create drag on it, so nothing to slow it down. So it just keeps going and going and going, and it loses momentum. It doesn't really lose momentum. But what's weird about that is there's other storms we watch storms form and disappear on Jupiter. So we're not sure. I guess the honest answer is we don't know precisely why the Great Red Spot has not vanished or moved away. It will kind of slowly glide around in that zone, but it doesn't like zip around the other parts of the surface.
Well, the red color is the red color specific to differences with the ammonia, or are there other components within that make it orange or red so vivid to the rest of the planet color?
There are, I mean, yeah, there are other components in there. Mostly it is the ammonia. It's really the ratio, the amount of ammonia versus hydrogen and helium, plus other trace elements. Again, mostly other things would be carbon dioxide, other hydrocarbons mixed in there. A lot of it has to do with the fact that because it's probably been in one place for so long, most of the hydrogen and helium has kind of been thrown out of it. So it's probably mostly ammonia crystals with other stuff mixed in.
Oh.
Like if one of those other bands got caught up like that, they would probably like churn out all the hydrogen and they would get much brighter like that. The Saturn. Saturn's atmosphere it's also a gas giant. Like Jupiter, it's mostly hydrogen and helium. It does have these swirling bands on it, but they're not quite, obviously they're not quite as vivid and brilliant as they are on Jupiter, but they're still pretty cool. They are still moving around at hundreds of miles an hour. They're zipping around it. If you actually went out there with a spacecraft, you would see the surface physically moving. It'd be pretty spectacular. And here's an artist's impression of probably what the surface would look like. This is actually an artist's impression of the Cassini spacecraft crashing into the atmosphere. About 2010, there was that Cassini mission that orbited around Saturn and took hundreds of cool photographs of the planet and its moons and the rings and everything. And eventually, at the end of its mission, they deliberately crashed it into the surface of Saturn just so they could get some final readings on what the clouds would be like. So this is just an artistic impression of what that's supposed to be. But it gives you an idea of a close-up view of some of those swirling clouds on Saturn. Now, one cool thing about Saturn here is at its North Pole, it has its own little, this huge hexagonal hurricane on there. Some of that image is false color. Of course, those blues are the ring that's been false colored to differentiate them from the planet. And this hexagonal storm is not quite that brilliant red, but they enhanced the image to make it clearer. So, but it actually is this weird hexagon on the surface, and it maintains that shape. And this is another thing that's sort of a mystery. Like we have a pretty good idea that the reason it maintains this odd geometrical shape is because of jet streams and fast moving winds up on the northern part of the planet that kind of like push and shepherd the clouds into that shape. The exact mechanism isn't precisely known, but that is their best guess right now, is that storms and winds are moving in this shape. So there's still a lot of cool mysteries out there related to the planets. Now, as I said, Uranus, the next planet out, it's actually our first of our ice giants. It's the blue-green, the very vivid blue-green color here is actually cold methane gas. Methane is the same kind of gas that you use in like in a gas stove, or not like, yeah, or in like various things produced by naturally on Earth, like from volcanoes. And out here, this far away from the sun, methane is actually cold enough that it will actually partially crystallize and form ice. So you'll get a lot, and there's a lot of it in the atmosphere of Uranus. It'll give it this kind of soft blue-green color. This picture of Uranus here has been a little bit enhanced, so you can see some of the bands in the color. It's tends to be more of a soft, almost whitish green color. But this enhanced image gives you a good look at the this also has swirling bands on it, because it is also subject to intense winds whipping around the surface, blowing those clouds of hydrogen and cold methane around at hundreds of miles an hour. And last planet, Neptune, also an ice giant. It's actually, compared to Neptune, or compared to Uranus, Neptune is actually a very vivid blue color, a real bright, almost like baby blue. And again, that's because of the frozen methane ice in the atmosphere. Though it's not quite sure, we aren't exactly sure why what the color difference is. One of the planets obviously has something else in its atmosphere that is giving them the different colors. It's possible that there are other components in the methane clouds of Neptune, possibly ammonia, something else. But again, it's one of those mysteries of our solar system. We haven't really been out to explore Neptune enough to know exactly what's going on there. But now Neptune is considered the windiest planet in our solar system, because this planet has the fastest moving winds that are whipping around at like 300 miles an hour. And again, the reason these winds are so fast is because there's no rocky surface to slow them down. They just pick up as the planet's orbiting, and they go faster and faster, and they just build and build and build for pretty much millions of years and just become these monster hurricanes. Now, one thing I want to go back to is, where is it? Let me close these out. One thing I'm sure you noticed while I was showing you the gas giants is that these images will go away. There we go. Saturn here, well, it doesn't have very bright clouds. It does have these fantastic rings. And actually, all of the large planets have rings. Saturn, Jupiter has rings, Uranus and Neptune. But with Jupiter, Uranus, and Neptune, they tend to be thinner bands that are kind of hard to see. Saturn, though, has these real bright signature bands. These bands, or these rings around Saturn are actually made out of ice. Thousands or millions and millions of tiny particles of ice. Some of them are big as a grain of dust, some of them the size of cars. But when you pull back this far, all of those ice grains just look like a ring. But if you were to like take a spaceship and dive into that, you would see the individual pieces up close. Now, even though there's these rings, you can see the circumference of the rings are actually much wider than Saturn itself. So they're very wide, but they're actually only a few miles thick. So comparatively, it's almost like a razor's edge on the ring, which is caused by their orbit around Saturn. Because as they're spinning around them, pulled by the gravity, they tend to flatten out into this disc-like shape. And we believe that the rings of Saturn, and in fact the rings of all of the gas giant planets, were formed when some sort of object got caught into the gravity of the planet and ripped apart. With Saturn, it's probably that like a large body of ice, like a comet, or even like a small moon, got pulled apart by Saturn's gravity and just broken up into ice that's spread out throughout and forming these rings. And then with like the same thing with Jupiter. Jupiter has a ring, which is probably a planet that was pulled apart and just spun out around it. It's likely that if you were to find a gas giant in another solar system, they would probably have the same thing. Of course, now the question there, then that begs the question, why doesn't Earth and why don't the other terrestrial planets have rings? And the idea, and we think that the reason that we don't find rings on Earth or Mars is just that they're not big enough. So objects that got pulled into our gravity, rather than being pulled apart and broken up into a ring, they would just they would either drift off into space, or they would just be sucked down into the atmosphere and burn up as a meteor. But we don't have that big enough mass where they hit that sweet spot where they just break apart and stay in orbit. So, all right. Let me just okay. So moving on from atmospheres, I'm going to talk about the magnetic fields of the planet. See, every planet has every planet is basically like a large magnet. With the terrestrial planets, they have a core made out of like liquid iron and nickel that's moving, it's orbiting, and it's actually moving at a different rate from the outside of the planet. And because due to some cool physics, that actually builds a magnetic field around the planet that projects way out into space. These blue-green lines you're seeing here are like a rough idea of what our magnetic field looks like on Earth. It's actually, the lines of the magnet are actually being blown back into space by radiation coming off of the sun. So the sun is actually creating a sort of what we call a solar wind blowing on it. But the magnetic fields of the planets, especially for Earth, are, well, for us being on the surface, are extremely useful because they actually deflect a lot of the solar radiation. If you were on a planet like Mercury that has or actually I should say on Mars, that has a very small magnetic field, you would be exposed to a lot more solar radiation because there's no magnets reflecting it. And here's a slightly better kind of schematic of the radiation belts here. The magnet within Earth, it creates kind of like a loop from the North Pole to the South. If you've ever, like in a science, if you were when you were a kid, if you ever did like the experiment with the magnet and the iron filings, you'll notice that the filings line up from the North Pole to the South Pole of the magnet. Same thing with Earth on a larger scale. And solar wind blowing off of the sun is actually deflected around those magnetic fields, keeping us safe from that. Though, one cool effect is that as the solar wind passes over Earth at the poles, the north and the south, the magnetic fields actually pull this radiation down towards the surface, which gives us, is it going to do it? Which actually gives us our auroras. There we go. One sec. There it is. Okay, so that green ring you can see whoop, there we go. Perfect. So these are the famous aurora borealis. These are caused by solar radiation being pulled down towards the surface of the Earth up in the northern part of the sky, or the southern part of the sky. So you can actually see aurora down in Antarctica too. And what's happening is, as the solar radiation or the solar wind is pulled down towards Earth, it energizes particles in the air. So it's actually like you've got nitrogen, oxygen, other gases, carbon dioxide floating around in the atmosphere of Earth. As the solar radiation hits that, as it's pulled down, it infuses them with energy, and those gases will actually start to glow, and they'll glow in different colors. So here, so if you see like the kind of rare magenta or blue colors, those are actually nitrogen. But a lot of times you see the aurora and it's green and red, and those are particles of oxygen that have been energized by solar wind and are lighting up. And as it ripples across the sky, the ripple is being caused by the just the waves of the solar radiation hitting the atmosphere. Here. Now, other planets also have magnetic fields, and they also, because of that, they also will. Some of them have auroras too. Earth has a magnetic field. Jupiter and the large gas giants do. And with their case, they don't really have they don't really have like a rocky core or like an iron core, but because they are so large and the way their clouds interact in the interior, they also become like a big magnet. So they have their own huge, massive magnetic fields orbiting around them. And in fact, we have spotted auroras on the surface of Jupiter. This is a slightly enhanced picture of auroras on the south and north poles of Jupiter itself. And it's likely that there also are auroras on Saturn. They have not been directly observed, but there's good circumstantial evidence that they exist. Now, Mars, like Earth, does have a magnetic field. It's a lot fainter on Mars, so Mars might have auroras. We don't know. We have never seen them. There might not be enough magnetic radiation, magnetic force there to create them. Yeah. So from magnetic fields and atmospheres, going to move on to the interiors of the planets. So here we're looking at all of the terrestrial planets. They're all similar composition. You've got the core, which on Earth's case is made out of the core of Earth is made out of liquid iron and nickel with a more solid core on the outside. Then you have the mantle, which is magma. It's liquid rock that is churning around the core. And then, of course, you have a thin little crust of solid rock on the surface, just a few miles thick on the surface. Now, with Earth, most of our planet is made up of the mantle with a solid or like a liquid core or a solid iron and nickel core in the center, like a big humongous ball of iron and nickel. And most of that, then beyond that, there is a liquid core of iron and nickel that orbits around it, and then a relatively thick layer of magma forming the mantle and the tiny crust. The surface of Venus, though, we've done tests with radio and other equipment, and we found out that Venus probably has a much larger core than Earth. So the liquid or the solid inner core is actually a lot larger than it is here. With a mantle's about the same size, but the center of it is a lot bigger. Now, what's interesting is Mercury, relative to its size relative to Earth, Mercury has a comparatively much bigger core. It's almost all core, as you can see in that picture there, which has had some interesting effects because Mercury is mostly iron nickel core. That iron nickel core is churning inside of the mantle as the planet orbits, and that's actually creating a huge, relatively huge magnetic field. So Mercury has a relative to its size, it has a very strong magnetic field due to this large core churning inside of it. Now, Mars is mostly cooled off. It's got a small core inside of it, but there's not a whole lot of magma activity going on. There's really not much of a core at all. Now, the gas giant planets, again, are mostly made out of hydrogen, with the ice giants having methane gas and ices in the various surfaces. There is believed to be a small rocky core somewhere at the center of all these planets. It's very tiny, not even the size of Earth, maybe the size of the moon. But what's interesting is between the hydrogen gas forming most of the atmosphere and that core, there's an area where the hydrogen gets squeezed under intense pressure. the pressure is so intense that it actually turns the hydrogen, which is normally a gas on Earth, it gets turned into a sort of liquid, like a liquid hydrogen, which and it also, because it's squeezed so tightly, it actually starts to, the molecules are squeezed so tight together, they actually take on properties of metal, which means they can conduct electricity. So we say that there is a core, like a mantle of metallic hydrogen inside Jupiter and Saturn, and Uranus and Neptune. Now, the thing is, honestly, we don't know what that would look like, because that doesn't exist outside the surface, outside anywhere on Earth. The only reason it can exist in Jupiter, Saturn, and the other planets is because there's so much pressure down there. So, and we actually haven't observed it directly, but theoretical models of what the gas giant planets look like suggest that that's what the interior is. So, from interiors, we're going to move on to the surface of the planets. So now the terrestrial planets, here we go. The terrestrial planets, of course, have a rocky surface, and most of the terrestrial planets are covered with craters, like you see here on the moon. These craters are caused by meteors, asteroids, space debris slamming into the surface for millions and billions of years. Most of the terrestrial planets have craters, actually all of them, I should say, have craters like this. The moon, of course, is our best example that we know of, just covered with craters. If you look at a picture of Mars, Mars is packed with craters. Mercury has craters on it. It actually looks kind of like a miniature, darker version of the moon, or like a darker version of the moon. Venus probably did have craters on it, but Venus's surface is so volcanically active that a lot of the craters get covered up right away by lava. And what I think is kind of cool is that Earth actually has craters on it, and Earth does get hit by asteroids relatively often, not constantly, obviously, but it does get hit by asteroids occasionally, and it does leave craters on the surface. Let's see here. Let me get a picture of one. If we fly away from the moon, go over to Earth, one of the most well-known and easy to see craters is, I want to be inside it. Let's see if I can find a picture of it from space. Oh, no, here we go. There it is. Whoa. All right. Do you want to come up for me? No. Always wants to land on the surface for some reason. I'm trying to get a view from space here. There we go.
May I ask, how often do asteroids hit the Earth?
Yeah, well, it's comparatively every couple hundred years. Well, actually, we are being bombarded by meteorites all the time. That's what shooting stars are. So if you go out most nights, you'll see a couple of meteors streak through the sky. Most of them burn up in Earth's atmosphere. Occasionally, a few of them hit the surface. The Barringer crater, which I'm trying to pull up here, is let's see here, is well, these are moon craters, but the like large craters or large objects hitting the Earth are comparatively rare. Like they happen maybe every couple thousand years. Asteroids especially are extremely rare. Like the asteroids that we have, like large, devastating asteroids rarely hit Earth. Mostly when you get craters on Earth, it's because of large meteors. I'm just trying to see if I can find it. Here we go. This is not quite the image I was looking for, but this will give you an idea. These are spots where meteors have struck Earth recently. So these are areas we have identified meteors on the surface of the planet. And actually, I know where I can show you a good picture. Let me just jump up here real quick. One sec. Ah, here we go. This is what I was looking for. There we go. So this is the Barringer crater. It's out in Arizona. It was struck by a large meteor, I think about 1,000 years ago. You can actually drive out to this. It's out in the middle of the flat plain. It's very cool. There's a little visitor center on the surface there, right on the edge. Another famous crater is this one here called the Manicouagan Reservoir up in Canada. What happened here was when a meteorite hit millions of years ago, it actually impacted the surface, pushed it down, and then debris filled in the center of the crater. And then around the debris, eventually it was flooded to create this cool little ring here. And actually one of my favorite Earth craters is this one here called the Nordlingen, I hope I'm pronouncing this right, Nordlingen crater. It's in Europe. There's actually a small, I believe it's in Austria, but there's a small town in the middle of it. It might be Germany, so don't quote me on that. But Nordlingen, it's the outside edge, the circular edge is actually the edge of the crater, and the whole town is built inside of it. So those are just some of the more well-known Earth craters, but there are several hundred of them on Earth. A lot of them are so eroded that we only know of them because we do sonar images of under the Earth. All right. So craters are one thing that can affect the surface of planets. Again, all planets get struck by meteors. They have craters on them. The moon is covered with craters, like you can see here. The moons of the outer planets are covered with craters. Ganymede, Europa, Mars has tons of craters. So anywhere you've got a solid body, you've got craters hitting it. And of course, the gas giants don't have craters because there's no gas, there's no surface for them to land for the craters to strike. Let's just get this off here. So craters shape the surfaces of planets in dynamic ways. There are other forces that shape planets. And a big one is volcanism, volcanoes. Now, on Earth, of course, we've got lots of volcanoes, the very famous ones. Let's see here. These green pyramids here are these are all the sites of all the major volcanoes spread throughout the Earth. And you'll notice that they cluster around like the edges of the continents here, and occasionally you'll get some that are in the middle of the ocean. Volcanoes appear usually at the end of what are of tectonic plates. The surface of the Earth is made out of huge slabs of rock that the continents sit on, and the ocean floor sits on as well. But the continents are resting on the surface of these huge tectonic plates that are slowly churning and grinding over the surface. They're actually floating on top of the mantle, and as the mantle churns, it moves them around. So you imagine like a bunch of rafts floating in a pool. They're all bumping it against each other. And there's multiple plates here. There's a large plate under North America, a plate under Africa, several plates under Asia, Australia. Wherever those plates hit and start to push against each other, you get tectonic activity. So you'll get earthquakes, you'll get tsunamis, you'll get volcanoes. The volcanoes are formed as the plates start to push together, and then lava, magma from underneath the surface just to bubble up where those plates are bumping together. So that's why you get them along the coasts here, because these coasts are the edge of those huge plates as they slide around. Of course, some of your more famous volcanoes are, oh, it's going to fly down again. Didn't want it to do that. Let's do this instead. Well, one of your more famous volcanoes, of course, you've got Mount St. Helens here when it blew up, I believe, a couple decades ago. Massive explosion through lots of gas and dust from the interior of the Earth. So what volcanoes are effectively doing is they're churning up material from inside the planet and blasting into the atmosphere. So lots of volcanic gas is all the stuff that's in the mantle being brought to the surface. And they can actually have major far-reaching effects on the climate of the surface. In addition to adding gas to the atmosphere, if they're particularly severe, they can actually affect the climate. One of the most well-known eruptions was Mount Tambora, which was in Southeast Asia. What happened there was this huge volcano erupted, throwing lots of ash and dust in the sky. That was about, let's see what was that exactly? That was in 1815, sorry. 1815, Mount Tambora in Indonesia erupted, throwing tons of gas and dust into the sky, and it actually covered the atmosphere for the whole year. So the sky was very dim and full of ash, and this actually created an overall cold climate around the Earth for about a year. And so that time was actually known as, in Europe, it was known as the year without a summer, because it never, like spring and summer kind of were passed over because it was so cold all the time. Now, just a little interesting anecdote regarding the eruption of Mount Tambora was the year without a summer meant that a lot of, there's a lot of, unfortunately for a lot of people, there was a lot of famine and, chills because crops couldn't grow because of the ash in the sky. In Europe, a lot of people had to take shelter inside all the time because it was so cold. And one group of Europeans, a couple of European aristocrats led by a man known as Lord Byron, he got some of his friends together at his chateau, his friend Percy Shelley and his young fiancée Mary Shelley, and a couple other people. And they all were kind of stuck in Byron's, admittedly nice chateau throughout the year without a summer, just stayed inside all the time. And they're trying to find ways to relieve their boredom because they can't go outside anywhere because it's too cold. So one night they all decided to have a ghost story writing contest. So each of them would try to write the scariest story they could to see if they could frighten the others. And the most famous story to come out of this was written by young Mary Shelley, who was 18 at the time. That was the novel Frankenstein, which is here we have an early illustration from the book from 1830. So Frankenstein was inadvertently caused by the eruption of a volcano, which is a pretty cool little fact, I think.
That's a very cool fact. I'm gonna have to bring that up just in polite conversation sometime. That's great. Yeah.
Mm-hmm. Yeah, I think it's really neat.
Yeah.
And in a way, like Mary Shelley's book is considered one of the first modern science fiction novels. So in a way, the eruption of Mount Tambora kind of started modern science fiction. Let's see here. Now, of course, close these guys. Close these guys off. All right, so now there are volcanoes on. So anyway, there are volcanoes on other planets too. Mars had volcanic activity. We don't think it does now, but is that gonna work for me? No, but it did have volcanoes at one point. On the surface here, you can see these three like pimple-looking dots there are extinct volcanoes on the surface. And right next to it, there's a large depression there. or actually it looks like kind of like a large bump. That is actually what's called Olympus Mons, or Mount Olympus, and it is the highest volcano in the solar system. It's just a huge mound of lava that's been building up for millions of years. And like the volcanoes on Earth, it was formed from magma and bubbling up under the surface. But Mars does not have tectonic plates. There's no plates moving around like rafts. It's just one solid crust. So here we think that the volcanoes formed just from the mantle kind of pushing up on the surface until it actually cracked through it and burst out onto the surface. But because there's no tectonic plates moving around, the volcanoes just stay in one spot. So they keep building and tossing out more and more lava for millions of years. So you get these massive volcanoes. Here's a good picture of Olympus Mons. And you can see the volcano itself is almost the size of the state of Arizona. It's huge. Now, the funny thing is, if you were down on the surface of Mars and looking at Mount Olympus, you probably wouldn't even realize it, because it's big, but it's also very flat. It's what's called a shield volcano, because it looks like a big, like, Roman shield, because the lava spread out very slowly on a long surface. And just so made this huge mound that rises up real high, but it's so gradual you won't even notice. And just to give you an idea of the scale, here is the largest volcano on Earth is Mauna Kea in Hawaii. And then compared to that, you have Mount Everest, of course, and then Olympus Mons rises up over almost 3 times as high as Mount Everest. So huge volcano. Now, here. Now, these are not the only kind of volcanoes in the solar system. A very cool kind of volcano is what's known as what we call a cryovolcano, or an ice volcano. See, of course, on the terrestrial planets, the stuff spewing out of the volcano is lava, liquid rock. Out beyond the asteroid belt, where all the gas giants are, they have moons that actually have volcanoes, but there it's so cold that those moons, like the moons orbiting around Jupiter, are mostly made out of ice with a little bit of rock on the inside. So there's not any lava inside them to push out to the surface. But they actually have these volcanoes that will push ice out from the inside. What's happening there is they actually, as these moons are orbiting around the planet, like say a moon of Jupiter, like Ganymede, is orbiting around Jupiter, the gravity of Jupiter is actually squeezing on the moon. As it squeezes, it actually pushes the ice out from underneath it up to the surface, like somebody squeezing a tube of toothpaste. So you'll get these like ice lavas flowing onto the surface. And of course, that doesn't exist here in the terrestrial planets because it's too warm. But you get way out into space, way out beyond the asteroid belt, and stuff starts to get really weird. And then you have geysers out in space. This here is the surface of the moon Enceladus. Enceladus is an ice moon orbiting around Saturn. It's mostly got a crust that's mostly, it's an ice crust, like a big thick glacier covering the whole surface. But we think there's actually an ocean of liquid water underneath it. I think the ice holds it in there, but the squeezing of the gravity of Saturn squeezes the planet till it actually forms cracks, and then the cracks produce geysers of this salty water from underneath gushing out onto the surface, which is what these blue streaks on Enceladus are in the picture. And we've actually taken pictures of these geysers right here, shooting off to the left side there. That's actually geysers spouting this salty ocean water out of the bottom of Enceladus out into space. The Cassini probe, the one I showed you earlier, that orbited Saturn, it actually passed through these geysers and took samples of the water, which was pretty cool. Let's see here.
So it was really salty, or what did they find within that water?
It is salty, kind of a lot like the Earth's ocean water, because what we think happened was, of course, the water itself was probably formed from like melting ice. And there's probably a rocky core underneath this water. And so as the water like erodes the rocky surface, it salts come out of the mineral solution and they build up in the water. So like on Earth, you get salty, the ocean is salty because of minerals breaking down on the land. With salts come out of the minerals and are washed down by rivers. In this case, with Enceladus, the ocean was eroding the rocky surface inside of it, and then that caused salts to dissolve into the water. So what's interesting about that is we know on Earth, at least, wherever there's water, there's life. So a lot of astronomers and astrobiologists are excited about these moons that have this moon that has water under the surface. And we think a lot of the moons of the gas giants might have a liquid ocean underneath it. Enceladus does, because we saw the geysers. Europa, Ganymede. We think a lot of the icy moons, and there are a lot of them, there are dozens of them, we think that they might have oceans of, at least some of them have oceans of liquid water underneath them. And we know, at least on Earth, water often equals life. So some people wonder if there could be things living in these oceans. Now, of course, we haven't found anything. We found no proof. We haven't gone close enough to see, but there are actually people who've proposed sending probes to these moons to drill down into the ice to see if there's something under there. So exciting stuff. As far as I know, there's no specific mission yet, but they talk about it a lot. And people at NASA especially are really excited about the idea. Let's see here. Now, another factor that influences the surface of planets is erosion, which on Earth is caused by water and wind. Oh, wants to pull in again. Huh? So here on Earth, a major thing that causes erosion are glaciers, what are basically rivers of ice. This is the Wrangler Glacier in Glacier National Park, and it is pretty effectively it is a flowing river of ice. The grooves that you see in there, the dark colored bands, are actually dirt that has been picked up as the glacier moves through the mountains. The glaciers do move just extremely slowly because they're ice, but they are flowing down towards the bottom. And as they move, they scour the land. They pull up boulders, they carve mountains, they carve out huge valleys. And here on Earth, we have a lot of features that were carved by glaciers. The Great Lakes are on Michigan. They give them that distinct thumb mitten shape. All the Great Lakes were carved out by glaciers scooping out the land. If you've ever been to the Finger Lakes region, the Finger Lakes were formed by glaciers digging troughs through a soft ground. And but it's not just liquid water that erodes land. You also have, there we go. You also have rivers, like liquid water eroding the land. This is an example of a river delta. This is the mouth of a river where the river has actually carried sediments down as it empties into the ocean, and it produces this huge delta, this huge swampy bayou area, like the end of Louisiana, where New Orleans is an example of a delta, or the Egyptian Nile Delta, where all the sediment that's picked up by the river as it winds through the landscape is dumped at the base there and spreads out, forming land. And farther up, the rivers will actually carve huge, deep canyons through the landscape. Like the Grand Canyon in Arizona was actually carved by the Colorado River. If you look way down at the bottom of the Grand Canyon, there's a river flowing down there. It's actually carved all the Grand Canyon. Over time, it's just eroded the land down, and the land's just collapsed and been eroded away just by that little river at the bottom. And sometimes when there's erosion, you'll get some pretty spectacular sights. Like this here is called Bryce Canyon. It's an area, I believe, it's in the Four Corners area. So I can't remember if it's in Utah or in Colorado, but it is a big canyon that was worn out originally by rivers flowing through it, and carved out these odd shapes in the rock. And then the shapes were further altered by wind blowing through there to make these odd looking columns and towers. And that's all just caused by wind and water working on the land over time. Whoop.
So were the rivers that small, or were they a lot wider? And then as they started sawing down, they just got tinier? Because it's really small at the bottom of the Grand Canyon.
Well,
Not wide, I should say.
they were a little wider, but they were not. It's not like they were huge like the Mississippi. Usually, what happened was the river cuts down into the land, and as it cuts down and forms a valley, the sides of the valley cave in.
Just fall
And
in.
it just keeps cutting down and cutting down and cutting down, and then the sides will collapse and just get wider. So the river, it was a little bigger. It doesn't shrink by that much, but it wasn't like a massive river that kind of shrunk down. It's more just like the sides have collapsed in. But it just shows you the power of how much a river can cut down into the landscape. And actually, here in Connecticut, the Connecticut River has actually done that. If you look at, like a good example is in Glastonbury, there's areas where if you can go along the river and you'll see you're up on like a high, like almost like a plateau, and you're looking down at the river. That's because the river at one point cut down through the landscape, and then the banks just sank down and eroded away. And let's see here. Now, water erosion also occurs in other planets. Mars at one point had water. We do know this for certain at this point. We've looked at Mars, we've taken lots of pictures of the surface, and we found features that are obviously river and like little erosion marks from water running downhill. Let's see here. Mars even has obvious river deltas. This is a false color picture. It's black and white with color added to it, but this is a river delta, a dry river delta on Mars with a big crater in the middle there. So at one point Mars did have water, liquid water on the surface. We're still not sure if it still has liquid water. Like, it definitely does not have as much water as it did. Like, there's no active rivers right now, but we think millions of years ago in the past, it used to have rivers. And what mostly happened was we think that some of the water evaporated into space because Mars's atmosphere is so thin. And a lot of it probably also got frozen in the soil. The soil of Mars is very mushy and very like slushy because it's got lots of ice particles in it. Let's see. But at one point in the past, we think that Mars did have, again, active bodies of water, and it might have even had oceans. Here's like a hypothetical Mars covered about 50% with water. We have evidence for this because we saw the river delta on the surface there. And actually, the northern part of Mars is a very flat, open plain, which is a sharp contrast to the rest of the planet. And we think that might be because that was the bottom of an ocean. That was the bottom of an ocean that was like smooth from all the sediment on it. And then eventually it evaporated away. Here is another close-up on the surface of Mars, showing you a very obvious river deltas cutting through the surface right there, dry riverbeds. And on Mars, we also have wind erosion as well. Like here on Earth, I mentioned briefly, we have wind that erodes down mountains and will erode shapes into the ground. One of the most prominent wind features on Earth are huge sand dunes, like in the Sahara Desert, or the Great Sand Dunes in Michigan, like Sleeping Bear Dunes. Or even here, if you go along the coast, like in Rhode Island, you'll see huge dunes formed by wind eroding the land. Mars also has wind erosion, and it has its own dunes. These triangular shaped objects here are a series of dunes on the surface of Mars. So now Mars, no, Venus and Mercury don't really have these features though, because Venus is too small to really have, his atmosphere is so thin that it doesn't really have wind or liquid water on its surface. So it's mostly just a dried up ball covered with craters. And Venus, the surface of Venus is constantly being remade by volcanic activity. So any like erosional features would quickly be covered up by the lava. But there are objects out in the farther parts of the solar system that do have erosion features as well. This here is the moon Titan, which orbits around Saturn. Titan, again, it's considered a moon because it orbits around a planet, but it's a very planet-like object. It's a world in its own right because it has an atmosphere. It's the only moon we know of that has a thick atmosphere, which is mostly nitrogen with carbon dioxide. And it also actually has signs of erosion. Titan actually has lakes on it. This is not the best picture, but this is like a sonar map of Titan. What you see here, these darker patches, are rivers and lakes, but they're not made out of water because it's too cold out where Titan is. Titan's orbiting around Saturn. It's so far away that water doesn't survive in liquid form. These are actually lakes of what are called hydrocarbons, like methane and ethane. Normally on Earth, those chemicals are gases, but here on Titan, they turn into liquid and they flow out as rivers, and you get huge lakes of these hydrocarbons acting kind of like the water does on Earth. And in fact, the ground here is ice. So the ice there it's water ice, and it's so cold that it actually acts like the rock of Titan. So it's tougher and more solid than Earth ice, and it can erode on its own. It can erode just like Earth rocks. So pretty cool. Titan is a very unusual world. Let's see here. We're gonna zip back to Mercury. Yeah, this is the planet Mercury. Going back to the inner planets here. If you notice here, it looks a lot kind of like a dark version of our own moon, covered with craters, which are those little bright spots there. And I just came back here because I forgot there is one there was one interesting erosional feature on Mercury, which are called they're called scarps, and they are these like buckled, not really mountains, but they're like little buckled plateau landscapes. These are caused by the surface actually sort of wrinkling. Like if you like left an orange out on the counter too long, the surface would wrinkle up. And that's what's happening here with Venus or Mercury. The surface is actually forming into wrinkles. And the reason we think that happened was because Mercury actually shrank in a distant past. When it was first formed in that early embryonic universe, solar system, it was a molten ball of lava. And as it cooled, it shrank down. And as it shrank, the surface bunched up and wrinkled, forming these scarps. So kind of a neat feature on the surface that we don't really find in other planets in the solar system. Let's see here. Let's see if I can get a good look at that. Second. Here we go. Here we go. Moons. All right. So we talked about the surface of planets, and now let's talk. Moving a little fast there. Let's talk about the objects that orbit around the planets, moons, which, like we saw with Titan. Whoa, moving a little fast there. We saw with Titan. Moons can often be worlds in their own right, even if they are orbiting another planet. Here we've got our own Earth's moon. And again, like before, we see that I want to turn around for me. There we go. So moons often form when, well, they form in different ways, but the most common way a moon forms on the terrestrial planets, well, on Earth at least, is when our specific moon, what happened was early in the formation of the solar system, when everything was still molten, we think another smaller planet, or a planetoid we call them, smashed into Earth, and rather than it, parts of it broke apart, but then it also got stuck in the surface of Earth. All these pieces were blown off, forming a brief ring. Again, Earth was too small to hold a ring for very long, but this debris condensed together and collapsed until it formed into another body, which is our moon. So our moon is made out of chunks of this other object, which we call Theia, and it's also made out of pieces of the Earth that got blasted off into space. We've got some evidence for this because we found rocks on the moon which are chemically identical to rocks on Earth, indicating that they are once part of the Earth. But then we have other rocks on the moon that are chemically a little different, and we think those are the pieces of Theia that remained. So our moon formed that way. Other moons, like the moons of Mars, actually has two moons, Phobos and Deimos. Those moons, we believe, are actually captured asteroids that were probably moving by the planet, and they got caught in its gravitational pull and orbited around it. Now, Venus and Mercury don't actually have moons. So Earth and Mars are the only terrestrial planets that do, and they have very few moons. We only have one. Mars has two very small ones. Now, moving fast there. Now, Jupiter and Saturn, there we go. All the gas giants and the ice giants have tons of moons. I believe Jupiter has four, what we call the Galilean moons. The four biggest moons are Ganymede, Callisto, Europa, and Io. Let's see here. But there are several hundred, there's at least, I think last count was 76. I don't know the exact count, but there are tons of other small moons orbiting around Jupiter. A lot of these are captured asteroids or chunks of meteors that are orbiting around the planet. But if we go back to the four big ones, Ganymede, Io, Callisto, and zoom in there. Ganymede, Io, Callisto, and Europa. Those are all balls of ice, again, with probably a liquid ocean underneath and a small rocky core. Those were probably formed similar to how our Earth's moon was formed. They were formed by chunks of debris and ice orbiting around Jupiter that got pulled together by the forces of gravity until they collapsed into a ball. Now, they didn't crash into Jupiter's surface because Jupiter doesn't have a solid surface. More likely is that these balls of ice were pulled into Jupiter's orbit, and they all kind of collided with each other and stuck together, like packing a snowball, until they became a moon. Now, the closest moon to Jupiter is Io, right here. Io is an interesting moon because it is actually a rocky surface. All the ice in the surface was boiled away millions of years ago, and it's actually covered with volcanoes. It is the most volcanically active body in the solar system. All those pockmarks you see all over it, those are huge volcanoes spurting lava on the surface. And here is actually this is an infrared image of a volcano actually erupting on the surface of Io. Let's see if I can find the other picture. Here's a better one. Here we go. Here's a picture of invisible light. This bright plume you can see on the surface is actually a volcano that's erupting on the surface of Io. And the reason it's so volcanic is because Io is very close to Jupiter. And what's happening is Jupiter, the gravitational pull of Jupiter is tugging on it and it's squeezing it. It's what's called a tidal friction because the gravitational pull, creating these it's pulling and pushing on it like this, kind of like you're squeezing like a basketball. And all that squeezing is creating pressure on the inside of Io, and that pressure generates heat. And all that heat comes out on the surface in the form of volcanoes. So all this pressure squeezing on the moon makes it the most volcanically active place in our solar system. Europa, which is a little farther away, is your more typical ice moon. It's got a surface that's just a solid sheet of ice with more than likely has a liquid ocean under the surface. And those scratch marks on it are actually those are rifts and cracks where the ice has been kind of pushed together and formed ridges. So this here is color enhanced. They're not quite this bright, but this shows you these rough ridges where as the ice was sliding against each other, they kind of pushed up and created these like track marks. They look almost like somebody was dragging a sled across the surface, but that's actually where like the ice is starting to rub against each other and fracture. Even the largest planet in Jupiter's system is Ganymede, and it's actually the largest moon in the solar system. It's actually this moon, Ganymede, is actually larger than Mercury, but it's classified as a moon again because it orbits Jupiter. It's mostly made out of rock. There's a rock interior, but there's an ocean underneath the surface with a thick layer of ice on top, which is also like Europa. It's crisscrossed with stress ridges from ice butting up against each other. And one thing you might notice is there's very few craters on the surface of Ganymede and on the surface of Europa because that ice is constantly in motion. So any craters quickly get smoothed over by the ice. Let's see here. And then this here is Callisto, which is the second largest of the Jupiter's moons. And then this one actually has mostly like Ganymede. It has a mostly rocky interior with a layer of possibly liquid ocean, and it's got a more of an even mixture of rock and ice on top, which is why it looks dirtier and darker because there's lots of dust and rock mixed into the surface ice. And moving out from Jupiter, we move to Saturn. We're going back to Titan again, and Titan is an ice, again, just to reiterate, Titan is an icy moon, mostly made out of water ice that's formed into like a rocky layer with oceans of hydrocarbons on them. Oh, here we go. This is actually a true color image of the surface of Titan. At one point, the Cassini probe dropped a lander on the surface, which took this photograph here. What you're seeing there is the atmosphere, which is mostly nitrogen gas, giving it that orange color. And you're seeing what look like rocks here are actually huge chunks of ice spread out across the surface. And then, of course, we've got, moving out from Titan, we've got Enceladus, another moon. That's the one with the tigers, with the stripes on it, where the geysers are coming out. Here's another good look at those geysers. We can actually see them blasting off into space. And just a quick look at Uranus and Neptune also have moons. And a lot of their moons are probably what we think are captured Kuiper belt objects. So they're miniature dwarf planets or small chunks of ice related to Jupiter, related to Pluto and Eris, that have been pulled in towards the inner solar system by the gravity of the ice giants. This one here is an interesting planet, interesting moon. This is Triton, a moon of Neptune, the largest moon, in fact, which was most likely a large captured dwarf planet. And we think that it might also have those, let's go into the dark side. But we think this also has cryovolcanoes on it from frozen nitrogen pushing out from under the surface. Let's see here. talked about rings already a little bit. Saturn has the famous bright rings, but Jupiter also has some thinned out rings. This here is actually a close-up of Saturn's rings, where you can see these individual bands made out of ice. That weird looking little kink in the middle there, that is actually a moon orbiting in the ring of Saturn. It has a number of objects called shepherd moons, which will orbit through the ring and actually push out material. It'll scoop up ice and push it off to the sides. So you'll get these little gaps in between the ring. And what's kind of neat is these shepherd moons, because they're pushing through all that ice and a lot of it collects on the surface, they will get this little high ridge around the center that makes them look kind of like a UFO or a walnut. So these are actual pictures of the moons Pan and Atlas. And you can see they got that ridge of ice around the center that they've collected from pushing through the rings. Now, here we go. Now, here we can see this image shows you the rings of Uranus, which again they're very thin, not as spectacular as the rings of Saturn, and they are mostly probably made out of like chunks of rock. So they're probably formed by a meteor getting caught in the gravity of Uranus and ripped to pieces. This is a slightly enhanced version of Uranus's rings that we're looking at here. Here you can actually see that there are the bright parts right there are actually very, very thin diffuse rings. Like you can't even see them in normal light, but with this color enhanced version, you can see that there's this thin rings of debris orbiting around Uranus from stuff that's hit it and is spread out into a ring. Neptune has rings too. They interestingly, you can see that Neptune has several different rings. There's a thin or thinned out, spread out inner ring, more tighter outer rings, and these are all kept in place by more of those shepherd moons. There's probably moons around there that are scooping out the ice in between them and kind of keeping them in this nice ringed orbit. And these rings, unfortunately, are probably not going to last. Well, are not going to last very long because they're so thin. All the particles of ice are gradually being lost to space. So that's going to keep happening over millions of years. So millions of years from now, Neptune and Uranus will probably lose their rings. Let's see here. So I've been mentioning asteroids and comets a lot. So what are those exactly? Well, we've got, they want to come up for me? Here we go. So we've got the asteroid belt between Mars and Jupiter. It's pretty famous. If you're a Star Wars fan, I'm sure you've seen the Millennium Falcon diving in and out of asteroids. An asteroid belt here in our solar system, there were a lot of theories for years of what caused it. For a long time, people thought that it might have been a planet between Jupiter and Mars that was destroyed and pulled apart by gravity. But what we've actually found is basically what's happened here is the asteroid belt was formed by Jupiter. The gravitational pull of Jupiter sucked in asteroids and meteors that were orbiting around in the solar system, and it kind of flung them into this orbit near Mars. But those objects that got too far in, closer to Earth or Mars, were sucked into the surface, were eventually sucked into Mars and Earth's orbit and crashed onto the surface. So the asteroid belt is basically made up of asteroids that have been pulled in by Jupiter, but they haven't been flung out of orbit so far that that Earth and Mars have sucked them up. So what's basically happening is Jupiter and Mars and Earth are shepherding these asteroids. They're clearing out any that get too close in, and any that drift too far out are pulled back in by Jupiter's gravity. So as cool as the idea of it being another planet, a destroyed planet is, it's really just lots of asteroids being shepherded into one place. But there are asteroids that orbit outside the asteroid belt. There actually are asteroids throughout our solar system. It's just that the asteroid belt is when they're most concentrated. An interesting kind of asteroid is called a Trojan. Trojan asteroids orbit in front of and behind Jupiter. And these are asteroids that are actually, they've been caught in, they've hit Jupiter's orbit in such a way that rather than being flung into the asteroid belt or sucked into Jupiter, they're caught in this weird orbit where they follow Jupiter around. They'll move, they're pushed along in front of it, and then they're tugged along behind. And there's a lot of physics going on there, a lot of stuff to do with gravity, a lot of equations, but they've fallen into just the right area that, again, they're not flung out into space. They're not pushed into the asteroid belt. They're just right, just following along Jupiter. Let's see here. So this is a artist impression of a space probe traveling to one of these Trojan asteroids. What's cool about the Trojans is they are thought to be remnants of the earliest part of the solar system. These are probably rocks that were formed around the same time that the Earth, Mars, and all the terrestrial planets were forming. These are just basically what these are is remains of other objects that never formed into planets. They didn't get thick enough to actually form a circle, a stable circle. They were just little chunks of dead planet. And this is a artist's conception of what a probe would look like investigating one of these Trojans. And another kind of asteroid is called a near-Earth asteroid, an NEA, because there are asteroids orbiting near Earth. They're far enough away that they only rarely hit us, but they are orbiting kind of around us, and they have been picked up in Earth's gravity. Again, Earth doesn't have as thick gravity as Jupiter, so they don't follow along in front of it or behind it. They just sort of kind of hover around it, occasionally giving a little tug by the Earth. But they aren't, again, they're in a situation where they're close enough to Earth, the Earth's gravity pulls them along, but they're not flung out into the asteroid belt. So there's all these regions of asteroids where they're all just in the right position, that gravity affects them in certain ways. So if you bring them all up here, you see the Trojans, the asteroid belt, near Earth asteroids, just all making this big complicated dance in the inner solar system. And sometimes asteroids will move out of one area into another. Sometimes Trojans will be pulled into the asteroid belt. On rare occasions, asteroids from the asteroid belt will be blown out into space or pulled towards Earth. But overall, they all tend to stay in these stable orbits. So there's this complicated dance going on.
Do you think they ever run into each other?
Oh, all the time. Yeah,
Okay.
they're always running into each other and smacking into each other and breaking
Yeah.
apart. Yeah, oh yeah. They're definitely doing that, bouncing off of each other.
Cool.
Let's see. There we go. And then when we pull out the Kuiper belt, it's kind of similar to the asteroid belt in that it's a body of, in this case, icy bodies, icy objects that have been pulled into an orbit by the sun, orbiting around it. Kuiper belt objects that get too close to the inner solar system are either picked up by the gravitational pull of Neptune and Uranus and flung into the center of the solar system where they're burned up as they get close to the sun, or they drift away off into space and just drift out of the solar system. So the Kuiper belt is this nice little area where they're in a stable orbit around, these bodies of ice are in a stable orbit around the sun. And going back to the dwarf planets, Pluto, Eris, Haumea, Makemake, these are all names for other ice planets out there. And a lot of these are balls of ice from the Kuiper belt that have just gotten so big that their own gravity has pulled them into a ball shape. So they become dwarf planets. So there's kind of like this continuity between like large balls of ice getting bigger, becoming dwarf planets. If they got big enough, they could become, and they cleared out their orbit of all debris, they could become a full planet. But they're all, kind of the same. There's like a continuity. So like the distinction between planet, dwarf planet, ice ball is really just labels that we've given these objects so we can categorize them and understand them. There we go. And going back to the Oort cloud is also a cloud of orbiting ice. But this orbits out farther from the Kuiper belt. And again, this is where a lot of the comets come from. There's Halley, Hale-Bopp. They were chunks of ice from way out in this diffuse Oort, O-O-R-T, Oort cloud that they got close. They got just close enough to the sun that the very faint gravitational tug of the sun pulled them in enough that they started forming these really elliptical orbits. So they go way out to the Oort cloud, back in towards the sun, and then back out towards the Oort cloud again in these long journeys that can take hundreds of years. And as they get closer to the sun, they actually start to melt. So they'll produce this tail, which is made, well, they actually have two tails. One tail is made out of melting ice, so water and bits of dust that is being blown off. It's actually not being blown out the back. A lot of pictures of comets, it looks like they've got a tail trailing behind them. The two tails are actually at an angle. So as the comet's going this way, they're kind of blasting off to the side because the two tails are being blown by the solar wind, the radiation coming off of the sun. So you've got one tail, which is made out of melted ice and dust from the comet. And then you have a tail of, it's a thinner tail. It's almost like a little laser beam coming out of the bottom. That is being formed by gas that has been energized by the solar radiation. And that's blowing off in a different direction. Because that's actually being deflected by solar radiation. The melted ice tail is being blown by solar wind, and the energized tail is being blown by solar radiation. But comets will eventually wear out because as they get close to the sun, they melt a little bit with the ice particles melt away. So eventually they can just completely melt away to nothing. Or occasionally they will actually strike the surface of a planet. Like this picture, well, this is not the best picture of it, but those white dots up at the top there. Oh, no, wait. Yeah, the white dots up here, those are actually spots on Jupiter where a comet broke apart and actually crashed into the surface of Jupiter and left these temporary little white dots when it plunged into the surface. Now we have actually gotten probes close to comets to get a better look at them. These are several examples of comets. And one thing you'll notice about them is they're all very uneven looking. They look like potatoes or like root vegetables. That's just their icy, rocky core that's just been partially melted, and it's mostly made out of like chunks of ice that have been fused together. The one down there on the lower right, Hartley 2, it's got these jets of melting ice that are actually shooting off of it because it's so close to the sun that the interior is starting to melt and just blast off of it. So I've been talking about our solar system. This is the place we know best. It's got all the planets, stars in it. But this isn't the only place in the universe that has planets, of course. Science fiction's always talked about other planets. And we've speculated for a long, hundreds of years that there were probably other planets out there. And we, of course, within the last couple of decades, we have actually found good evidence of exoplanets, planets out beyond our own solar system. And as the technology has gotten better and better to identify them, we found hundreds of them. Every one of these little blue dots or blue circles is a exoplanet. outside of our solar system. So then we find a lot of, this is just an estimate, it's kind of a weird little graph, but that's just an estimate of how many different types of other planets we found. Most of the ones we find are large gas giant planets because using the instruments we have, those are the ones that are easiest to spot. Earth-sized planets are a little harder because they're so small. And usually the way we detect a lot of exoplanets is we look at a star and we see, we have to use very advanced telescopes and fine-tune equipment. We can see if a planet passes in front of the star, it will dim the light of the star for a few seconds. It can grow dim, and when that happens, we can calculate based off of that how big the planet is. Again, this is all very, very, very refined equipment doing that. But using these methods, we've been able to find, again, hundreds of planets throughout the galaxy. And as the equipment gets better, we've actually been able to figure out what types of planets they are. We found gas giants. We found worlds that are probably mostly water. We found super Earths, like rocky Earth-like planets that are several times the size of our Earth. We found weird stuff. Like we found planets that are probably rain liquid metal on the surface. We found planets that look like Jupiter, but they're orbiting close to their sun, like in the orbit of Mercury. A lot of weird stuff out there. So, and we're really just starting to explore exoplanets, and hopefully within the next couple of decades, we'll learn a lot more about them. So that's our tour of the planet and the overview of planetary science. So again, sorry about that little hiccup in the beginning there, but at least we got it going. Anybody have any more questions for me? I'm happy to answer questions.
You did an awesome job.
Thank you.
I'm on overload with all the info. It was just phenomenal. So
yeah.
Thank you so much.
Mm-hmm.
And I agree, and thank you for allowing me to jump in an hour late. It's just the way the evening went, but thank you. That was outstanding. I look forward to watch the recording of the first hour and see everything.
Oh yeah,
really
I'll make sure that we have a copy available.
Okay,
Mm-hmm.
thanks.
Mm-hmm.
Thank you.
Yep. And I know that was like a lot of stuff to absorb, but you can always watch the recording. And in addition, I'm doing another class next month, and we'll also be doing I don't know if you're on Facebook, we do Facebook Live shows on just for the public on the Facebook page. So if you go to the Glastonbury Planetarium Facebook page and look on videos, Jason and I have done them pretty much every month going back since 2020. We got different topics. We'll do star talks about constellations. He's done a couple on like the International Space Station, the space race. So definitely check those out too.
Great.
Mm-hmm.
Excellent.
Yeah, outstanding. Yeah.
Thank you so much.
Thank you.
All right.
Have a nice evening.
So we can come and see you at the Glastonbury Planetarium sometime.
Hopefully someday. Yeah, I would love to do public shows. But I've got to wait to see what happens with the pandemic. But
Yeah,
someday we'll definitely get back to it.
that's good.
Mhm.
Well, we appreciate what you're doing.
Yes, very
Well,
much.
thank you so
Thank you.
much.
Thank you, everyone. Good night.
Have a
Good
good
night.
night.
Here. Thanks again.
Mhm.
So long.
Have a lovely night.
You too.